Let's kick it off with this statement from Jensen Huang, the CEO of NVIDIA, which he said at the beginning of this year at CES in Las Vegas, the ChatGPT moment for general robotics is just around the corner. And if you look through your LinkedIn timelines, you may see a pretty impressive demonstration of robots which are doing some backflips or sorting some laundries. I think even in one of the presentations before, we saw the robots from Figure AI doing some classical household tasks. It looks like we would be near at the moment where we have humanoid robot working in our factories. But if we look in the reality, and we go especially in small and medium enterprises, then we see that there is a lot of manual labor. So we still have, or in large enterprises like automotive, we see industry robots we have since decades. But the general breakthrough of robotics is far away. And I want to take you on a little journey on how the intelligence of robotics is developed or has developed over the last years. And with this, I want to give a short notice about the Fraunhofer Gesellschaft, where I'm working for. We are one of the largest applied research organizations in Europe. And I'm with the Fraunhofer Institute for Material Flow and Logistics in Dortmund. And we have the mission of doing 100% of logistics. So we are dealing from the supply chain up to intralogistics, and we are building pretty cool robots for logistics use cases. And I bring one robot with, today, which is the EvoBot. And I hope it keeps you awake before the lunch break, because the EvoBot is a highly dynamic robot which has some bio-inspired features and is pretty flexible to perform different tasks. It uses the principle of a doubled inverted pendulum, and we can use this for different tasks. You can see the EvoBot here handling some stuff at an airport. We can drive it indoor and outdoor. So we have a lot of applications. And in all these applications, EvoBot gets its balance and is able to handle things. And thanks to its bio-inspired design, it's pretty friendly to the humans. So people walking around with the EvoBot, they really like it. And you can see we can even carry some garbage cans. But how do we get robots which are performing such tasks? I want to present you 3 steps. But first of all, we need to start with the robotics foundations. And to be fair, even if we're actually telling a lot about AI and robotics, most of the stuff in robotics is today without AI. So if we just want to put EvoBot in a warehouse environment and let it drive around, then we can do it mostly with the foundations, which relies on optimization, about control theory, or even probabilistic methods. We can see here 3 examples. So the control of the EvoBot, for example, these are classical control approaches. If we look about localization, where we use the LiDAR technology, this is often probabilistic methods. And if we do path planning and navigation, this is mostly classical algorithms as well. So on the right, you can see the Load Runner, which is a swarm robot we developed at Fraunhofer AML for sorting tasks. And most of this pre-planning of trajectories are done without any kind of AI. This is quite beneficial because in robotics, we have hard real-time requirements and we have limited onboard resources, so sometimes it's a good idea to not use AI. But if we want to do more things like handling stuff, we really have a benefit on AI. The first one is already more than 10 years before, and all of you know. So in computer vision, we had in 2012 CNNs, and these machine learning neural networks are already really dominant in perception tasks and with these uses in robotics as well. So you have here a bunch of videos where we, for example, segment some things in a bin for bin picking applications. We can detect pallets, so we can track pallets to grab them autonomously. So a lot of things can be done with AI over the last years, and this was even an enabler for robotics in different applications. Then we saw a second step, which is the idea of bringing more robots to different applications. So it's something like bringing robots into the wild. So we now have much more diverse different robots. So for example, you can see in this image that the EvoBot could be now put to a desert environment where we have an uneven ground, which makes it much more complicated to drive around. We can have robot dogs, like we know from quadrupeds, like from Boston Dynamics. And we even have humanoid robots nowadays. Most of these robots learn based on learning-based approaches like reinforcement learning. We already have seen it in the talk about before with safe deep reinforcement learning. And this enables us pretty cool demonstrations. Like we have here this robot dog, which can do parkour. It's a demo from ETH Zurich, or now Robotics on their animal robot. We can use this robot for inspection tasks. Then we have a humanoid robot doing some crawl stuff. And on the right-hand side, finally, after the advertisement, sorry for this, we see a video from Olympiads which have taken place a few weeks before in China, where we see different robots competing in different Olympics tasks. And these humanoids you see they're running are mostly trained on these learning-based tasks. The funny thing is you can see the people running next to the robots because they're not acting autonomously. There is a guy with the controller. And we have, with these learning-based approaches, we have robust policies for complex environment. We can even apply this to our own robots, to logistics robots. So for example, for the EvoBot, we have the problem of handling different packages with different loads. And if we want to have different payloads, we combine some classical control approaches with reinforcement learning-based approaches to have a more flexible adaptation to different tasks. And most of this stuff is learned in simulation, because in simulation we can create so many environments and so many scenarios, and then we can train the robot to behave robust in a real-world environment. And for the simulation, I have another example, which is a pallet transporting robot, which is called Odin. Odin is capable to drive pallets with an outstanding speed of up to 10 meters per second, indoor and outdoor. And thanks to abilities we have today, like GPUs and really nice renderings, we can build a complete digital twin of the robot in simulation. So you can see in this video that we have replicated most of the parts of Odin completely in the simulation, and we can use this to speed up our robotics development, because we can train AI models, and we can, for example, parallelize hardware and software development. And you can see we can give the same driving behaviors to the real robot and to the simulated one, and both behave the same. And we even have physical collisions we use for the omnidirectional movement of the robot in simulation. All of this is quite cool, but we have the problem that if we want to put a robot from one application to another, it's getting more complicated, because we often then need a system integrator, or we need to completely change the behavior of the robot, train our AI models completely new. And there we have some new potential thanks to the rise of generative AI and foundation models in the last years. Oh, I missed one point. So we could now put the EvoBot from our logistics warehouse to an airport. And the idea is that I don't need a system integrator for this, but that just a worker who is working with the EvoBot is now able to tell him, please now go outside and don't handle packages anymore, but grab the luggage and help me transporting the luggage. So the idea is that the robot becomes more a colleague than a machine which is fixed in their applications. And for this, I have a great example from the colleagues from the Fraunhofer IES. And they stated to simply talk to the robot. Because when we see applications from cobots, for example, we need code to fulfill different tasks. And the idea of the agentic system developed here is that we can just talk to the robot. So my colleague told him, OK, please stack the chocolates based on the colors. And the robot is able to generate some code, as we all know from Copilot. But then we have a system which is directly a code interpreter which checks if the code which we have generated is valid. And then we can put this code into valid robot actions, and then the robot can perform different tasks. We combine this with foundation models like vision language models, And so we can put up a monitoring agent, and this monitoring agent is constantly checking our camera stream if the robot is performing the task correctly. So if the robot would, for example, put white chocolate on the stack for the red chocolates, then it can give some feedback that we should correct this one. Another example we have in this manipulator area is an agent we developed for another use case where we have packages where labels are put on the packages. And in this case, you have an interface like you know from ChatGPT or other agentic systems, and we can just talk to the robot. In this case, we just ask him, please give me the apples. And then the robot is using the principle of tool calling, so it has different tools and skills like checking what is printed on the labels. And then it can use this one to identify the apples, and it can use other skills like grabbing a package or combining different tools to fulfill tasks. Here we can see it in a live demonstration, and there we just a visitor of a fair came by and asked the robot to sort the things based on healthy and unhealthy. And the agent is able to understand, okay, on my workbench there are apples, quinoa, and nachos. And so first of all, it grabs the apples. Now as a second option, it takes the quinoa and says, okay, both of these things are healthy. So I put them on one stack. Then it is, okay, there are nachos, they're not so healthy, though as a last option, it takes the nachos and places the nachos on another stack. And this interaction is completely flexible. So you could go to this demonstrator and ask him, okay, tonight a friend is visiting me and we want to do a movie night. Can you give me something for our movie night? And then the agent is understanding, okay, a movie night, maybe it's better to have nachos instead of apples, and then the robot will give you the nachos. The cool thing is we can apply these principles to manipulators, but even to much more different robots. So for example, we can put it to mobile robots, like you will see shortly with the mobile manipulator. And we're even talking to companies like, for example, Kion, a supplier or one of the biggest suppliers for intralogistics solutions. And there we're checking out how we can use generative AI and agentic systems for improving the commissioning of their forklifts. And this next example is from a project at the Lamar Institute for Machine Learning and Artificial Intelligence. And there we are checking to improve order picking. Because if we want to do order picking, we mostly use some humans for the order picking, which just grab a paper and check what they need to grab. Or we have a completely optimized solution. But we want to have a mobile manipulator for order picking, a bit like a vacuum cleaning robot. The vacuum cleaning robot, you just put out of the box, and then you drive the vacuum cleaning robot one time through your flat, and then it is able to get commands like clean my kitchen. And the idea of this project is that we use a mobile manipulator. The mobile manipulator is driving around your warehouse, and then it checks which items are available in this warehouse. And then you have an interface, and in this interface you check, okay, I want the 3 different parts, and then the mobile manipulator is driving into the warehouse and is grabbing the different stuffs and does the order picking for you. To conclude, what you have just seen is that, in my opinion, AI evolution is some kind of really pushing the robotics intelligence, and it enables us to do advanced automation. So we can now bring robots in different applications. Thanks to foundation models, which are trained on large data sets, we are now much more able to go to other tasks or to other domains. This is a huge improvement. But what we still see is that there is a gap between lab demonstrations and the real world. Because we see a lot of improvements in hardware and even in the models. As robots are cheaper than ever before, we have now more embedded compute performance. But if we really want to get it into application, it's some kind of difficult. And these cool videos you see of robots, for example, folding your laundries, this is far away from really being used, and these robots are really slow. And in robotics, we always have the trade-off. So we could use the coolest big AI models, which are running on big servers, and we could adapt to different tasks, but then we're not fast. And this is what we often use for robotics. And as it was already highlighted in one of the previous talks, a fast robot is not so safe for humans, and a slow robot is safe for humans, but it's not so fast. So we always need to deal with this trade-off. And I think we need to have a good business context and domain expertise to really develop useful robotics tasks. Because if I think about a general purpose robot, which is now picking up my old vacuum cleaning robot, which is still wired, and then going through my flat and doing the vacuum cleaning, this is not so smart. Why not using these vacuum cleaning robots we already have? Because we humans are not often the best choice for all tasks, and we use tools for having or to solving this task. So maybe it's sometimes a bit more useful to improve our tools instead of having a general purpose robot. For example, an EvoBot can much faster transport a package from A to B than a humanoid robot, because I think it's 10 times faster than a humanoid robot, actually. And the last point I want to mention, we shouldn't forget the human acceptance for robots. In an early prototype version of EvoBot, it had some kind of an angry face. And then we changed the face. It was so easy. It was just some 3D printing. And suddenly the people loved the EvoBot. So now if it is on fairs, kids are playing with the robots just because the face is more friendly. And to be fair, I would prefer to have, for example, Wall-E from Disney or a Pixar movie than a dystopic humanoid robot. With this, I want to conclude with 2 hints. First of all, we are part of the Fraunhofer Big Data Alliance for Big Data and AI, and we have a booth outside over there. And we have a new white paper which is dealing with generative AI in robotics, but even in completely different domains, as we as Fraunhofer have so many domains. So this white paper came out last Friday, so feel free to check the QR code and download it. It's completely free. And the last hint is we have the booth there, and on the booth there is an EvoBot. So make sure to step by and get a look on the real EvoBot. And there we have a demonstration, a demonstration of the EvoBot and the Odin robot in simulation. So you can grab a PlayStation controller and drive around with these robots in a warehouse. It's a lot of fun, so please take the chance and step by. Thanks.